Okay, so today we're gonna talk about shortest path algorithm, like one of the cornerstone of graph algorithms. Like it's underlying so many things like internet routing, Google Maps, and so on. Okay, first thing first. About the homework is due tonight, and don't forget to give the correctness and why your running time is as you claim inside your solution. So, shortest path, just the background, the notation. What we're gonna look at is the directed graph. So it's just a graph such that each edge has direction, okay? And each edge will have some length. So we will have a length function L. It's kind of the same as weight, but I just call it length, okay? And now for any path, the length of the path. So for any path pi, the length of the path is just a sum of the edge length along the path. For example, if this is vertex S, and this is T. I don't know. Okay, this is S and this is T. Then this is a ST path. It just go from S to T. Okay, and the length is just the sum of the length of all edges. Is it the shortest path from S to T? Well, it is because actually it's the only path from S to T. You cannot just go from here to here because it's directed. So what is we will call distance, ST distance or distance from S to T. It's just the shortest length from any path, for any path from S to T. So like the length of the shortest path. Okay. And now, is it actually well defined? Actually, there are two reasons that there couldn't be a shortest path from S to T. Can you tell me what are the two reasons?
One of them is if there's like a negative cycle, so there is no minimum because you could have like a negative infinity.
Yeah, exactly. Very good. Yeah, if there is a negative cycle, then you can kind of loop over that cycle and there is no shortest thing. Yeah. What else? Like there is another reason. Yeah.
There's just no path from S to T?
Yeah, exactly. Yeah, good. So yeah, the first reason is if there is no path from S to T, then it's like the distance is infinite. And otherwise, if there is a negative cycle, you can just loop over this and there's no shortest one. So it's like the distance is minus infinite. Okay, but usually we just assume that when we want to think about the distance from S to T, we just assume that this doesn't happen, these two things doesn't happen. It's kind of easy to check if there is a ST path or not just by doing breadth first search or depth first search. You can check that in linear time. To check if there is this thing or not is less trivial, and we will see how to do that actually today. Okay, there will be two main problems that we're going to look at. The first problem is called single source shortest path, or SSSP. Here we have a source, S is given, and what we want to compute is to compute distance from S to every other node T. Otherwise, there is a next problem called all pair shortest path. Here, we want to compute the distance between all pairs ST. So you might wonder, like, we call this problem shortest path, but why do we just want only distance? Like, it's just a number, not the path itself. So it turns out actually it's quite easy to tweak any algorithm that compute distance so that you get an actual path itself. So let's actually try to do this. The exercise that I want you to try to think is that suppose that you have already computed distance from S to every other node T. Okay. You have computed distance from S to every one. It's just a number for each node. How can you obtain the path itself? So I claim that actually what you can do, you can obtain a shortest path tree. It's a 3T rooted at S. And this tree is a subgraph of G. Like all this edge here are like all the edge of the 3T is an edge from the graph G. And what's more, you have the property that if you walk along from S to T in the graph, in the tree, let's say fix any node T here. If you walk from S to T, then this path itself is the shortest path in G. That is, the distance here in T is the same as the distance from S to and T in the graph itself. And so I claim that you can compute this tree in just linear time. M is the number of edges. Okay. Anyone have like a suggestion how to do that? Okay.
Maybe like a sort of breadth first search on the distances. So you push everything distance, or you push the root in, the source in, and then you push everything with distance 1 in, you like attach it, and then you push everything with distance 2 in and attach it to things with distance 1 away.
I'm not sure that works actually. There will be actually a simpler solution than that. So the first thing that I want you to see is that suppose that this is S and this is T. Let's say that this is a ST shortest path. Let's look at the last node. Let's call it X. Then you see that this subpath itself must be the shortest path from S to X as well, right? Otherwise, if not, then there would be a shorter one, and so like this path wouldn't be the shortest path from S to T. So what you know actually is that the distance from S to T is gonna be the distance from S to X plus the length from X to T. If, and actually only if, X is in the shortest path from S to T. Okay? And now, so suppose that now, like let's say that all I want to see now is just that for T, I just want to know who is like the second last guy in this path. How can I check that fast in, let's say, in the degree time, in time which is degree of T? I can just really scan through all incoming edges of T and really just check if this thing is the same as this thing. You see? Like, just loop through all the incoming edges from to T and just compute whether this condition holds. And if that is the case, then you know that this is my, like, this is gonna be my previous guy in the path from S to T. And if you do that, then what will happen? Then you have that for every node, you kind of know your parent. And which means what? Like, what you get is just some graph such that each node has some parents. And this node will have some parents too. And it will keep going until you stop at S, right? And every node will, like, as long as you have a graph where each node has one parent, you will get a tree. You will get a directed tree rooted at S. So you see, like, this is how you construct this tree, T. And the total time that you need to construct this tree is just, the time that you spend is just the sum of the degree on each node T. And that is just O of M, right? Does it make sense, this solution? Question about this? Yeah.
O of M would be, like what is M in this case?
M is the number of edges.
Oh, okay. But if you have a number of edges, then can't you just rerun the entire shortest path algorithm anyway?
So
If you're linear in the number of edges?
So it's actually not clear how to compute shortest path in just linear time. Like even Dijkstra algorithm takes you like something like m plus n log n, and if actually there is a negative weight edge in the graph, it's even not clear how to like. That's not clear at all how to do something in linear time. You can do it in linear time if the graph is unweighted, then you can do breadth first search and you get a. But here I want to say that, okay, if someone gives you the distance already, then it's actually very easy to come up with a tree. Okay. So yeah, it's really just kind of enough to compute the distance itself, not the path, not the distance, not the path itself. So question about this? More question? Okay.
Yeah, just to follow up.
Yeah.
So based on Dijkstra's runtime, like this is only better than rerunning the entire thing for a graph that's sparse.
That's
right?
sparse, yeah, right. Okay, good. So now what I'm gonna do is start with the first algorithm, how to compute the single source distance. And the algorithm is by Bellman-Ford. So if you remember, Bellman is the one who come up with dynamic programming. So kind of obviously, this algorithm is gonna be dynamic programming again. Okay. So the setting is that you have a graph and you have a source node. And let's say n is the number of nodes, m is the number of edges. And let's assume for now that there is no negative weight cycle. We will remove this assumption soon. And we will show an algorithm with this running time, mn. Yeah, so the key idea is to use dynamic programming. And the key object that we're gonna look at is based on this definition. I call it like barred hop distance. So like I hop barred distance from S to T is just the distance of like the shortest length of ST path that use at most I edges. Okay. So note that the graph have length now, but barred hop distance is just like you count here. You really just count the number of edges, not the length. Okay. So just to make it clear, you see that the barred hop distance for every ST is always going to be at least the real distance, right? Because you put more restriction into your notion of path that you allowed. So So the distance is going to be at least the real distance. The bounded hop distance is at least the real distance. And it can be much more than that, much more than the real distance. For example, if your graph look like this is S and T. Let's say there is this path of length 2. And there is this one hop thing of length 10,000. So you see that like one hop bounded distance is going to be 10,000, but the real distance is just 2. But okay, so it's not quite, it can be not something that we want because we want the real distance.
I'm a little confused. Like, where is this 10,000 coming from?
It's just some number that I put in this example. Just to give the example where this thing can be much more than this. We work on the weighted graph, so yeah, on graph with length. So that's the length of the edge. Okay, so now, so you see, it might not, like, bounded hop distance might not be what we want, but I claim that actually is, once the number of hop is large enough, then it's actually what we want. That is, if the graph has n node and doesn't have negative length cycles, then n-1 hop bounded distance is just the same as the real distance. And the argument is actually simple. This is just because suppose that your path, there is some shortest path that has more than n-1 hop. So let's say it has n hop. If it has n hop, it must hit like more than n nodes. So n plus 1, which means that it must repeat at some node by pigeonhole principle. But if it repeats at a node, then it must contain a cycle like this. But we assume that there is no negative length cycle. So we could have actually removed that. And we get like a path with less number of hop. So as long as your hop is more than n-1, actually there is like another path with this at least as better length as the previous one, but have less number of hop. That's why you can assume that any shortest path have hop at most n-1. So it's just enough to just compute this thing if you want the real distance. Question? Good. Okay. So now you see, like, now we can say that the goal is just to compute n-1 hop bounded distance from S to T for all T. Can we do this recursively now? Like, this is something that, like, this notion is the notion that kind of, we come up with this notion so that it's easier to come up with a recursive algorithm. And what we want to do is to now try to compute this thing in a recursive way. So that's my question to you. How can you compute the distance? Let's say you wanna compute I hop bounded distance from S to B. Can you compute it? Can you compute it using some table that contains like I-1 hop bounded distance from S to everyone? How can you do that? So I let you think for 2 minutes and then we brainstorm how to do this. So the goal is to come up with this like recursive equation. Okay? So try to come up with that.
Distance y minus 1 s to some point.
Okay, so any ideas to share? Have some?
I think so.
Yeah.
The distance or the IHOP bounded distance from S to V is the minimum of the distance from I minus 1 from S to any point plus the distance from that point to S. And so you can just check those M values or the number of points, N values, I guess, and see which one's the smallest.
Yeah, very good, thanks. So, yeah, just to kind of say what you said. So, actually, there is like kind of simple condition. So, if actually you know that the IHOP bounded path, the IHOP bounded shortest path, use just at most I minus 1 edges, then you can just put this distance to assign to this guy. It's just a case where you don't even use IHOP. But if you use IHOP, then you know that like this IHOP, shortest IHOP path must use like a sum, like I minus 1 edges first, and then there is a last edge. So what you do is just kind of look at all incoming edge from to V. It can be U to V, right? And you know that to go to V, it must be like a sum path of length I minus 1 hop to U. So how would you go to U? You just go to U in the best way. That is, just use a path that have length equals to the distance of I minus 1 hop, shortest path from S to U. And then just do the last step here. And that's just the best way to go to V through U. But now you can just range over all incoming edges. Like take a minimum over all incoming edges. That's going to be your solution. And now, once you have this recursive equation, and if we want to use dynamic programming, yeah, how many subproblems do we have in here? Yeah.
N squared M.
N squared M. Not quite right yet. Just because you see S here is actually always fixed.
Yeah. And M.
So, yeah. So, well, almost right again. Just because, like, this thing is just a node. So there are only N. Yeah, N squared. Yeah, thanks. So this thing range from 1 to N minus 1, 0 to N minus 1, and this is ranging, like there are N nodes, so it's N squared. But thanks for answering anyway. So, okay, so once you see that, okay, we kind of done with the first step, we get a recursive equation with small number of subproblems. Now just create a table and fill in the table, right? Always like this. So the table that we're gonna create is called this instead of memo because it kind of have meaning here. So the entry I and T will store the I bounded hop distance from S to T. Okay. And let's say that we initialize everything to be infinite. And what we know is that the best case is when you don't allow any path, like you only allow the path of length 0. So the only thing that is like that is not infinite is from S to S. The length is 0. And in the general case, what we do is just kind of try to just loop over all I, right, from 1 to n-1. Compute this for every node V. And just put this recursive equation that we had before from the previous slides. Okay. Well, the running time is going to be here. There are n loops. Oh, I forgot to say the last step is that what we return is we just return this n-1, this array. And we know that this is the same as real distance from previous slides. So that's the correct, that's why the algorithm is correct. And for the running time, there are n many loops. And for each loop, how much time do we spend? We kind of summing over all vertex V, but for each vertex V, we spend time proportional to its degree. Each vertex we spend different, varying time. We spend time proportional to its degree because we kind of range over all this. But that's just M. Yeah, the sum over all degrees M, like 2M. Yeah. So that's why the total running time is Mn. Okay. So that's Bellman-Ford. Like, it's really kind of, it's something that if you are now, by now you should be quite comfortable with dynamic programming. And it's something that actually, if you just start with this definition, you should have, if you spend maybe half an hour, you might actually can rediscover this algorithm by yourself actually. Okay. So that's Bellman-Ford in Mn time. Now, I said before that we want to we don't want to assume that the graph have a negative cycle. So what we want to do is to try to solve a harder problem. That is, if the graph has no negative length cycle, then just try to do like before, return the distance. Otherwise, if there exists a negative cycle, then just try to say, okay, report that there is a negative cycle. Okay. Now, how do we solve this? Well, one observation is that I want to claim that if V is in the negative cycle, then I claim that this thing is true. That is, the distance from S to V that use at most 2 n hop. It's going to be actually smaller than the shortest path that use at most n hop. Actually, something stronger is true, but I leave this as an exercise. Let's try to see why this is the case. This looks like some condition that we can check easily, but we need to see why this is true. Okay. So, anyone have ideas to share why this looks like something that should be true? Yeah.
But if the cycle is negative length, then you're just going to be like decreasing distance, right? So if you run through it more than once, it's going to be lower than your original distance.
Yeah, exactly. Very good. So let's say that this is S and this is V. Okay. So S, let's say that there is a path from S to V, right? And if V is in a negative cycle, so you know that this is at most n hop, and this is at most n hop. Actually n minus 1, and this is n minus 1 too. So this thing, like suppose that you use at most n hop, right, from S to V. You're gonna end up to V using at most n hop. But if I allow additional, like in addition to that, another n hop, what you can do is that you can always just loop through this negative cycle once more. You might loop through through this many times because the negative cycle might have less number of hop. But if I allow n more hop, you can loop through this negative cycle again for sure. And if you do that, then the distance that you get is going to be smaller. You see? So that's why this thing must be smaller than this thing. Like this thing itself might be negative already, just because it might be the case that there are you might take just one hop here and just loop through this cycle and become negative already. But if I allow you n more hops, you're gonna get even more negative. Okay, good. So you know that, okay, this is something that looks like something that we can check easily if something is in a negative cycle. Now the next thing is that, you see, Bellman-Ford algorithm itself always correctly compute the bounded hop distance for any I anyway. I previously assumed that there is no negative cycle just so that the distance is the same as bounded hop distance when I is n-1. But that's the only reason I need that assumption. But this algorithm itself, it can compute the bounded hop distance correctly, you see, always. So now, given these two observations, how would you try to check if there is a negative cycle? Yeah.
Just run the loop until 2n instead of n, and then at the very end you just check that condition for.
Exactly. Good. Yeah. Just run the loop until I is to n. At the end, just check this condition. If it is true for any node v, if so, then you just report that there is a negative cycle. So that's kind of easy. So this is the way to check that if there is a negative cycle in a graph too in mn time. Okay. Good. So that's it for Bellman-Ford for single source shortest path. But now we can kind of use the similar techniques for all pair shortest path as well. Okay. So that's next algorithm now. Okay. So now if we want to solve all pair distance, to compute all pair distance, one option is just to run the previous algorithm from every source. We would get all pair distance. But the running time would be mn for each time we run Bellman-Ford and do it n time. So that's mn squared. Well, can we do this? Can we do better? Yeah, of course. Otherwise, anyway. So how to come up with better idea? Okay. So you see, in the previous algorithm, the recursive idea that we had is that we want to compute IHOP bounded distance using some information from I-1 bounded hop distance. The question that I want to ask you is, can you compute IHOP bounded distance using just I/2 bounded hop distance? So I let you spend 2 minutes to try to come up with the recursive equation that you can compute I bounded hop distance based on I/2 bounded hop distance. And suppose that you have compute I/2 bounded hop distance for all pairs already.
That feels like it because it's like
Okay, so anyone want to share some idea? Anyone on the back, maybe? Or anyone else then? Okay, you can try.
Use like the same idea as the I and I-1. Like if the shortest distance from S to V using I hops is we actually use at most I/2, then we can take the I/2 path. And if it's not, then we can always split it into 2 paths of length at most I/2. So we can just take the minimum of all intermediate vertices, U, and then add it with the distance from U to V.
Yeah, exactly. Thanks a lot. So basically, this is the new recursion. You just know that, okay, any path must have a middle point. Any path where you have something in the middle. So what you do, well, suppose that I want to compute like a 2i hop bounded distance from S to T. So let's say that x now is in the middle. Then you can just try to compute like the distance here is gonna be at most the length of these 2 things, right? And each of these 2 things need to be like the best path using at most I hop from S to X. And this is the best path using at most I hop from X to D. Well, you don't know which one is the middle point of your shortest path. But if you hit it at the shortest path, it's going to be the correct, like this distance plus this distance is going to be your correct 2i hop bounded distance. But you don't know which one is the best x. Well, but you can just range like a just compute this for all x and take the minimum. X, one of the x will hit the middle point of the shortest path. Okay, so that's how you get this recursive formulation, such that like now this I just double each time you do a recursion instead of just increment by just one. So that's like a nice progress, right? It's just jump by like a factor of 2. One question though, like why couldn't we actually use this idea that seems good for single source shortest path?
We know how distances from any vertex to T.
Yeah, exactly. Like this recursive equation works under the fact that we have computed all pair distance before in the previous round, but here it requires like a distance from x to t, right? So it just doesn't work if we just want to keep computing single source distance. Okay, so and yeah, you get this recursive equation, and the number of subproblem that we're gonna need actually is gonna be quite small. So first of all, let's try to do that. Like this thing have n choice, this thing has n choice, so it's at least n square. But you need to range over all I too. But now the point is that the range of I is gonna be just log n many value that we need, because what we need is this n or n minus 1, but we can double this. We just keep doubling I, so just do this log n times, you're gonna reach this already. Okay, so that's why the total number of subproblem is just n square log n. That's like number of subproblem. So now what you do is just fill in the array. You create the table for this indexed by IST, and this should be okay. So this is like this of 2 to the I for ST, and for this equals 1, or I is 0. What you compute is just like the shortest path of length with one edge. So what you can do is just to put the length of one edge into each entry. So if there is an edge here, just put ST, the length of ST. Otherwise, you cannot go to S to T from S to T using one edge. So that's infinite. And if S and T is the same, then it's 0. Okay. Good. So now, now you just loop through this thing. Start from range from, put I starting from 1 to log n, and just compute distance from S to T using 2 to the I hop. It's gonna be this from this recursive equation that we saw before. And yeah, so well, at the end you return this n minus 1. And by the way, just to be clear, if n minus 1 is not a power of 2, that's fine, right? As long as you return this of some 2 to the I such that 2 to the I is more than n minus 1, that's already good enough. And yeah, so you don't actually need to assume this thing, but I just assume it for simplicity. Okay. What's the running time? Yep.
mn log n.
mn log n. Not quite actually. It's not quite mn. Like maybe try again. So there's one log n for sure, and this is n square. And to do this, you spend n time. So it's n cubed log n. Yeah. Okay. Okay, good. So now that's how you compute all pair shortest path in n cubed time, n cubed log n time. Okay, one question. I want you to consider one weird matrix multiplication. So let's say that I said that this matrix C is a matrix, like it's a product between A and B, and this is like some weird product. So it's a weird product in the sense that usually in normal matrix multiplication, the entry ST of this resulting matrix is going to be sum over all x and this thing you multiply, these two things you multiply. But now if instead I just replace multiply with plus and sum with min, it's just some operation, okay? And you know that given the matrix of size n by n, and if you want to multiply under min plus product like this, the running time is going to be n cubed if you just do it trivially. So you can just multiply, like compute each of this in n times. There are n square entry, you can compute it in n cubed time. Okay, so now try to stare at this matrix multiplication product, like this min plus matrix multiplication. And can anyone tell me like why this matrix multiplication have something to do with the previous algorithm that we have seen? You can like maybe say this thing, this thing. So you see, I mean, just without trying to think much, you can see that syntactically, they look just almost the same, right? This is min, this is plus, and if you want to compute this thing from like entry ST, it's just like do multiplication, min plus multiplication, when this is like just do min plus multiplication basically, where this is like just sx and this is xt, you plus and then do take the minimum. So what I claim is that just take this, all right, this is some matrix. You can think of this table as a matrix. Let me call this thing A, matrix A. It's just n by n matrix. Now, what is this thing? I claim that this thing is nothing but a to the 1, a to the n minus 1 when the multiplication is under this operation. So I won't go into more detail, but this view of algorithm is gonna be useful in your homework. So try to see how come this table is just the same thing as a to the n minus 1 when this multiplication, like it's just a times a times a n minus 1 times when the multiplication is under this matrix product. Okay. So okay, I just leave it at that. Try to see and understand this connection. So it's a nice way to see that this algorithm is nothing but just computing the power of some matrix. Like very succinct way to describe the algorithm, right? Okay, good. So that's the way to compute all pair shortest path. And I want to just go to one more all pair shortest path algorithm, just another classical one. It has some advantage. It's called Floyd-Warshall. Just because it's a bit faster, it takes n cube time instead of n cube log n. Okay, but it cannot detect the negative weight cycle. Okay, just to see about, to talk about this algorithm, I need one notation. So suppose that I order vertices into like v1 up to vn, just some arbitrary order. Okay. Doesn't matter what is the order. Now I say that the path pi, if the path pi starts from S in a T and has this thing in the middle, I call this vertices intermediate vertices or inner vertices of this path. Now comes the key definition. Let me call like this IST is a middle restricted distance. What do I mean by middle restricted? I mean that it's the shortest length of all path of ST path, such that it uses only V1 up to Vi as a inner vertices. It can use less than this guy, like smaller subset, but everyone must be only from this set. So again, you see, obviously, this n is the same as this when you allow to use any one. And for this I, but when I is less than n, then this is a restriction, so it might not be the real distance. This I ST is at least this ST. Okay. Now with this formulation, with this key definition, yeah, this is the point where maybe I let you try to come up with this classical how to solve all pair shortest path using this definition and rediscover this classical algorithm by yourself. I give you 5 minutes. Yeah.
Just to make sure, middle restricted distance requires the use of those as intermediate vertices, or is it up to that set of intermediate vertices?
Yeah, up to that set. Like you might not use every one.
Okay.
You can use just like maybe just V1 only. Yeah. If that is enough, if that is like shorter one.
Sweet.
Yeah. So the point is try to come up with some recursive algorithm from this definition.
It's like the NQ, right? It's just like simple NQ algorithm. Okay.
Yeah.
Okay, so anyone, did you rediscover this classical algorithm? Anyone? Yeah,
I have at least an idea. I'm not sure
sure.
if the runtime
Let's
is right.
try. Yeah.
Like the distance from S to T that uses only that set of intermediate vertices is the same as the distance from S to V1 plus the middle restricted distance of V2 to Vi minus 1 plus the distance from Vi to T. And so you can just keep recursing, like moving inward in the middle. But I don't.
I think it's quite close, not quite right yet. Yeah.
Like quite close.
Yes.
You can compute distance using up to I+1 using distance from only I, with like the same idea as we've covered before, like distance using up to I+1 from S to T is the minimum of a distance from S to Vi+1 using only up to Vi plus distance from Vi+1 to T using
Yeah. Good. Yeah. Thanks. So let me just try to say that once more. So let's say that we want to compute like this K from S to T. Well, you have two choices about Vk, whether like you want to use it or not. Suppose that you consider like a path from middle restricted path from S to T. Okay. If you know that you wouldn't use Vk, the last guy in the middle restricted set that you want to look at. If you don't use this Vk, so it just goes through this guy without using Vk, then you know that this is just gonna be the distance k minus 1 from S to T, because it just goes through this set without VK anyway. Otherwise, if you know that you need to use VK, then you can just go to VK first. But you know that the inner vertices of this path is going to be only from this guy, because VK now is like not the inner guy of this path. And then just go from VK to this, using everyone outside, using everyone from this guy. Again, because VK is not the inner one. So what you get is just this equation where you just go from S to VK, using only from the inner guy is just up to k minus 1, and from VK up to T, where the inner guy is just up to k minus 1. Yeah, so that's the recursion. And once you get that, then we can see that the number of subproblems we need to look at is just n cubed, because there are n choice here, n choice here, and n choice here. That's n cubed. And well, once you have that, just fill in the table, and that's it. Like, fill in the table. Well, like what you do is just starting from 0. This is a place where you don't allow any midpoint, any inner guy. So the only option is just to use an edge, or it's infinite. And in the general case, we just do what we did before, like just put the recursive equation here. Yeah. Everything here just take O1 time. And the loop is in total n cubed. So that's why the running time is n cubed. At the end, you return this n. And as we said, this is just the same as this. Okay, so that's how we are done with this. And yeah, that's n cubed running time. The state of the art for all partialist paths is that no one knows how to improve upon n cubed. There are a bunch of work actually that get you something like n over log n. I don't know what's wrong with this, but yeah. But right now, the best algorithm actually takes something like n to the. This is the best algorithm. This is a weird looking expression, but it's just something that still much larger than this thing, when this is a constant. But it is actually better than log to the 100 or any polylog. So it gives you some like a nice improvement that is faster than any polylog factor, but it's not polynomial improvement. So, and the techniques that they try to do is based on some circuit complexity approach. That's very cool work, and it's by William, I think from this year. I'm not sure. Yeah, Ryan William. So he's actually like complexity theorist people, but somehow he can make contribution to like classical algorithm like this. Anyway, this thing is not known, and it's remained one of the 3 biggest open problem in algorithm. Why? Because it plays a role similar to SAT and NP hardness. That is, like, if you can solve SAT fast in polynomial time, then there are like literally like 10,000 other problems where you can solve in polynomial time too. For APSP, if you can get something better than n cubed, it's not like 10,000 other problems, but something like 20 other problems that is important, and you can simultaneously improve all of them to be better than n cubed. So yeah, it's like a very nice problem to try. And some people conjecture that you cannot improve, but I don't believe that. So you can, yeah, it's like a nice problem to look at. Anyway, so far, you see that all shortest path algorithm that we have seen is just dynamic programming on graph. Question?
Yeah, I was curious. On the last slide, you said it was one of the 3 biggest open problems in algorithms. What are the other 2?
What are the other 2? Good. So the other 2 is, one is called, it's a weird name, but they call it three-sum problem. Three-sum. The problem is this. You have, let's say you have n numbers, and what you want to check is just whether there are 3 numbers out of your set such that when you sum them up, you get 0. That's it. And the best algorithm so far gives you something like n squared. There is some improvement to like n squared over log n. No one knows how to improve more than that. And if you can improve it to be like a n to the 1.9, then times like a 20 or more problem, you can improve that too. Yeah. Another problem is called orthogonal vector, but it's simple to state too, but let me not go into it. Yeah, three-sum is like a simple algorithm, a simple problem to state. Yeah. You see, right? Just n numbers, pick 3 numbers so that the sum is 0. Can you find that? Yeah. Okay, good. So yeah, so you see like dynamic programming is kind of pervasive and it works for like very nice problem like shortest path. So the next and the last algorithm that I want to just give you intuition without proof yet, we're gonna do it next time, is Dijkstra. And I guess can you tell me, like, have some of you seen this algorithm before? Can you maybe raise the hand? Basically, almost. Okay, but almost everyone, but I will just go through it again anyway. So this is like a fast single source shortest path algorithm, but it works only on positive weighted graph. But let's see the intuition of this. So one of the simplest way to solve shortest path, if the graph is unweighted, is to do breadth first search. What is that? Well, it's like you kind of start from a source S and look at the neighbor of S, go to the neighbor and call, and each of this is gonna be of distance 1 from you. And then you look at the neighbor of your neighbor, and that's gonna be the distance 2. Okay. Another way to look at this simple algorithm is to take the continuous view. Just imagine that you kind of pump some water into S, and it just keep growing a ball from S, right, in a continuous way. And start your timer at 0. And whenever the water reached some node T, look at your timer, and the distance of T is gonna be the time at the point that you reach T. And that is, the time is gonna be just exactly distance from S to T. And the time that you're gonna reach this guy, like just keep growing your water, and when the water reach this guy is gonna be at time 2, and so on. Okay. So you can think of breadth first search as like a discrete implementation of this continuous process. And kind of it's just the same idea when the same idea just work in weighted graph, and that's exactly what Dijkstra algorithm is. So let me give some example. Like suppose that what what's the water gonna look like at time 1? It's gonna reach this guy, and kind of just this is like kind of the length of the edge. So the water just reached this up to this point. And what's how the water look like at time 2? Just kind of keep growing a bit, and now it reached this guy and doesn't reach this yet, doesn't complete this path yet. Okay. And so on. Like you keep growing this thing. And the challenge is just that we don't want to just kind of do this continuous process. We want to see like what's the next. We kind of just ask ourselves, what is the next vertex that the water reach, so that we kind of know the distance of the next vertex. Okay. So whenever the water reach any vertex, the distance of that guy is finalized. Like we just look at the time and you know that, okay, that's the distance for that guy. We don't want to just grow everything. You just want to know, okay, kind of fast forward the time. What's the next guy that's gonna reach and at what time, and do that. So that's exactly what Dijkstra tried to do. So the algorithm is gonna be like, you have a graph, can be directed with non-negative length and a source, and you start this the distance to itself to be 0. Everything else, let's say, is still infinite, and there is a finalized set. The finalized set is just a set of nodes such that the water have reached. Anyone that water have reached, you kind of finalize. You know the distance. And yeah, kind of, you think of this guy as like a distance estimate, because how to say this? This thing will keep going down, like until, but for the one that is already finalized, this variable will not change. That's the one that is finalized. Maybe let me give you some more example. So, like these nodes are the node that is finalized because the water have reached them, and this is, I call this thing, like I color them red because they are finalized, and everything else, the blue guy is just the edge such that the water might flow into. Okay. And if you want to ask, okay, if you want to try to implement this continuous process in the discrete way, you basically want to ask yourself, which node will receive the water next, right? So can you tell me what is the next node in this case? Yeah.
It's marked with B.
Yeah, the B guy. Yeah. And why is that? Because B is the one that, like, with the shortest distance from S, that just when you use only like the red and blue edges. Okay. So, and what you're gonna do is just to go to B and make B finalize. And the time that you reach B, you can just like put it to be this distance. And by the way, like this kind of intuition works really well when the graph have no negative edge. Can someone we can just say B is finalized when there is no negative edge. Can someone tell me what actually goes wrong if there is a negative edge? Like why we cannot actually say that the distance of B is finalized? Yeah.
So if the distance from S to B is like say 1, the distance from S to A is say 2, and the distance from A to B is like -2, then the best path to B would actually to go to A.
Yeah.
And B.
So this is, let's say this is 1, and let's say this is even 10, and this is like a 1 minus 100. So it will reach, we would reach B first, and it would take like 10 times step before we reach A. B would be finalized already, but you see that actually there is like a shorter path that goes through this guy. So the point is that the analogy of trying to flow water through some pipe of length something just doesn't make sense when the length is negative. So just this physical intuition is just break. Okay. But this physical intuition looks good if everything is non-negative. So, and that's how the algorithm is gonna look like. So what you're gonna do is just try to repeat until all vertices are finalized. And what you're gonna do in each loop, you just look at the guy that is not finalized yet. Take the guy with minimum distance from S to U that is not finalized yet, and add U into the finalized set. So that U here is just the B guy from the previous slide. And once you get the vertex U, just try to relax. I'm not sure why they call it relax actually, but they call it relax. Relax this edge going out from U to V, going from U, you relax everyone. So this is just kind of to color it blue. Like what you do is kind of just color this thing blue. What do you do exactly? You just compute this thing. That is, for every node that you can go out of the node U, call it V, you kind of update this distance estimate from S to V. How? If there is a way to go from S to U, to go from S to V through U, which is better than your previous estimate, just update that. And then we're gonna just repeat. Okay, you have seen this algorithm, and what I add here today is just some more intuition. But what we're gonna do next is to really prove why this is really correct and show some fast implementation. Before I end, let me just digress again. This guy Dijkstra, like this algorithm is what he's famous for, right? But there is another reason that he is famous because of this quote too. He said that computer science is no more about computers than astronomy is about telescope. And that actually makes a lot of sense to me, especially if we add that this is like a theoretical computer science. Theoretical. And the reason is, you see, if you talk about what is computation, it's really something that's so abstract that is so universal. Like, so Avi Wigderson put it this way. Avi is like the grandfather is like really big guy. So Avi Wigderson, you can have a look. He said that computation is just any evolution process in some environment by a sequence of simple and local steps. And if you put it this way, you see the example of thing that can be captured by computation is just endless. Okay, one is bits in computer, or like a computer in network that kind of communicate to each other. But it can be like something else, like protein in the cell, cells in tissue, neuron in the brain, friend in Facebook, anything. All of this you can model, like theory of computation have something to say to all this thing. Like they all follow some algorithm, and that's why computer science is like really universal. Anyway, next time is gonna be Dijkstra and dynamic shortest path. So we're gonna look at dynamic algorithm.
Today was a light class.
Yeah, the pizza was in the